Okay, so if you guys remember from Wednesday's class, we were doing a titration, and we were titrating here in the burette. Okay, this is called the titrant. Okay, this is a continuation of our problem from Monday, and our titrant, if you remember, was NaOH. And then in the flask, we had HNO2. Okay, HNO2, and HNO2 is what we're going to call the titrand. Okay, so we did 3 problems so far. Okay, we did 3 problems involving this titration. Okay, one problem was where no NaOH was added or no titrant was added. Okay, that was one problem, and what do we get for the pH of that one? Okay, this is a continuation of that. We got pH of 2.17, and then we did a second problem, part B, where we did it before the equivalence point. So anybody remember what equivalence point means? Okay, the definition of equivalence point, what does that mean? Okay, it means this titrant is equal to what? The titrand. Very good. So you add enough titrant so that it equalizes, normalizes, completely reacts with totally all of the titrand. That is before the equivalence point, and we got an answer of pH 3.94, and then we had a doozy of a problem where we did it at the equivalence point. Okay, so what is the equivalence point? I think you mentioned, Leslie. I want to repeat it again. What are equal? Okay, those two are equal to one another, so completely, totally, all of the titrant completely, totally reacts with all of the titrand, and we got a pH of 8.02. Okay, what do we have to do special at the equivalence point? Okay, what do we have to use? Not the forward reaction, but the what reaction? The reverse reaction. Okay, so remember to do that for the test. All right, and now we will complete this window of the titration. The fourth and final phase of this titration is not when, no titrant added, before the equivalence point, at the equivalence point. What do you guys think comes next? Okay, after the equivalence point. All right, so that's problem, this one here. All right, so let's do a problem where we add enough NaOH, where what is in excess now? Okay, at the equivalence point, the titrant is equal to titrand, but after the equivalence point, what's in excess? What do you have more of? Titrant. Titrant you have more of, okay? So you keep on adding more and more titrant. This is increasing in concentration over that. Since OH minus is the titrant, what will you have excess of? You will have excess of OH minus. All right. So what is the pH when 105 mLs of NaOH is added? So let's review here. Okay, we got 100 mLs. This is our initial conditions. We have 100 mLs of 0.10 molar HNO2. All right, that is titrated against 0.10 molar NaOH. All right, and how much NaOH are we adding here? 105. All right, so we'll calculate the concentrations after mixing. First we'll do OH minus. So we have 105 mLs of NaOH, which is just basically OH minus. Okay, times what is the concentration? Okay, 0.10 molar. NaOH. What is our total volume? What's our total volume here? We added 80 mils and to how much? 100 mils. So what's 100 plus 80? 100, and then we add 80. Oh, I'm sorry. Strike that. We add 105 mils of NaOH to how many mils of HNO2? 100. So what is 105 plus 100? 205. Okay, does everyone see where I'm getting the 205? Okay, you add the volumes together. Total volume. Okay, and then the concentration of HNO2 after mixing. What's the concentration of HNO2 here? Okay, sitting in the flask, sitting as the titrand, is 100 mLs, 0.10 molar HNO2. And what's our total volume? Okay, 205 mLs. Okay, so the mils cancel. So what's 105 times 0.1 divided by 205? 105 times 0.1 is 10.5. 10.5 divided by 205. 0.0512. Is that what you guys are getting? All right, 100 ml times 0.1, I know that's 10. That's 10 divided by 205, 0.0478 molar. Is that what you guys are getting? Okay, so this is the concentration after you mix 105 mLs with 100 mLs of HNO2. All right, so what is the equation here? Okay, so HNO2, okay, NaOH is a strong base. It's a strong base, so OH minus. Okay, this is in an equilibrium. Okay, this strong base is going to abstract that proton, giving us H2O liquid and NO2 minus. Right, the concentration of HNO2 here is going to be 0.0478. The concentration of OH minus, is 0.0512. Okay, we don't care about water, and this is going to be 0. And I'll ask you this question, Allison. Okay, I'm going to put you on the spot here. OH minus, is that a strong base? Okay, it is. So how much of this HNO2 will it eat up?
All of it.
Yes, and how much is all of it?
0.0478.
Everyone see that? 0.0478. Okay, so this strong base eats up all of that weak acid. Okay, what's 0.0512 minus 0.0478? 0.0512 minus 0.0478. 0.0034. Okay, 0.0034 big M. All right, so instead of calculating the pH first, what should we calculate? Okay, what can we calculate? Before calculating pH, what should we calculate? Yes, sir. Very good. We'll calculate the POH. Okay, this is what happens after the equivalence point. Okay? POH. So POH is equal to minus the log of OH minus, which is minus the log of 0.0034. Okay, what is that on your calculator? minus the log of 0.0034. No. Minus the log 0.0034. Getting 2.47. Okay, that's our POH. That is our POH. So this is not our answer. What is our answer? Okay, we will take 14 minus that 2.47, and what will we get? $11.53. And this is our answer after the equivalence point. Okay, so what do you have after the equivalence point in excess? You have OH minus in excess. Okay. Before the equivalence point, what do you have? Before the equivalence point, you have a buffer that you can use the Henderson-Hasselbalch equation. And then at the equivalence point, you have a situation where you have to use KB, and I think, Leslie, you mentioned at the equivalence point you use the back reaction. Isn't it correct? Yes. Okay. After the equivalence point, you have excess titrant. In this case, the titrant is OH minus. Right, so this is how we do these types of problems. Okay, so we went through every iteration of a titration where nothing is added before the EP, at the EP, use the back reaction, and then after the EP, equivalence points. All right, so people may need a little extra help on what happens after, or at the equivalence point. So let's do another problem here, an example problem. We won't go over all 4 phases. We'll just do this phase. Okay, this is our next problem at the equivalence point. Okay. Another practice problem where we are titrating to a volume that is at the equivalence point. So do this along with me. Calculate the pH at the equivalence point. And the titration of 50 milliliters of 0.10 molar methylamine. Now, I'll give you this formula. Okay, I'll give you that. You don't have to memorize it. Okay, methylamine is CH3NH2. Okay, by the way, anybody here taking organic chemistry, there's a functional group that they'll teach you in organic chemistry. We talk about functional groups. There's alcohols, esters, ethers. Here's a functional group here, the amines. Okay. That's a functional group that you'll learn in organic chemistry. All right, so I'll give you the formula for methylamine with 0.2 molar HCl solution. So what type of acid is HCl? It's a strong acid, okay, and they want to do it at the equivalence point. Okay, so in this specific case, okay, here's our burette, okay, that long glass tube. This is going to have our strong acid, HCl, which is at 0.2 molar. And then in our flask, okay, the titrand, we will have 50 ml of 0.10 molar methylamine.
Is there any particular reason why it's like the acid in the burette and the base in the flask, or is it just, does it matter?
It's just a type of titration. Yeah.
So you could do it the other way, it doesn't make.
Oh, I mean, you can usually.
Like the base and the burette.
Usually, what they like to do, Allison, is have the strong here that you're reacting against the weak.
Okay.
Typically,
So
but you can do any titration against anything, really. Yeah, but you don't want to titrate an acid with an acid because that's. I mean, you could, but I don't know what information you gain out of that. In acid-based titrations, you titrate an acid with a base. So you're figuring out how much this acid reacts with how much of this base. Okay, that point is called the equivalence point.
So just the stronger one.
Typically, the stronger one goes up on top, yes. Typically. But there's no, I mean, you can titrate anything against anything, really. By the way, this is called an acid-base titration. Okay, there's different types of titrations. Okay, this specific one is called an acid-base titration. There's redox titration. If you take Dr. Hooper's analytical chemistry class, I think it's called instrumental analysis. She does all these, not acid-base. She'll do like, different types of redox or potential titrations, whatever. Okay, so this specific titration we're doing, or practice problem we're doing, is an acid-base titration. All right, so at the equivalence point, okay, remember here, just as a reminder, HCl is the titrant. And then this amine here is the titrant. By the way, this is a weak base. Okay, amines are a weak base. Okay, that's just something I'll tell you on the test. Okay, but you shouldn't. It's not OH minus, so it's a weak base. HCl, you should know, is a strong acid. It's one of our 6 strong acids. Okay, at the equivalence point, we have M1 V1 equals M2 V2 of the titrant and the titrand. This is at EP. So we have, let's see here, M1 of HCl. We'll do this HCl. We'll do this methylamine. So HCl, we have a molarity of 0.2 molar. Okay, we have a volume that we want to try to figure out. We have the molarity here of the weak base as 0.1 molar. And we have a volume sitting here in the flask as 50 ml. And what do we get for V1? I can do this in my head. It's 25 mLs. Okay, 25 mLs. It's some very blurry blue ink. Okay, so at the equivalence point, which I'm calling EP, okay, this is equal to that. So it takes 25 mLs. What a great pen. It takes 25 mLs of 0.2 molar HCl to react with 50 mLs of 0.1 molar methylamine. Okay, completely react with. Okay, completely. No excess, anything. No excess, nothing is left behind. All of this reacts with all of that. Okay, that is what happens at the equivalence point. All right, so now let's write our equation here. So this is a strong acid, as Alice had mentioned. So there's 2 ways I could write this. Okay, there's 2 ways I can write this. I'm going to write it this way. Okay, I have my methylamine here. Okay, this is a strong acid, so it's 100% what? It's 100% H plus. Okay, but I'm going to write that H plus as H3O plus. Okay, this is this. Okay, this is this because it's a strong acid, 100% source of protons. Okay, this is the reaction that occurs. Okay, what does an acid do? Okay, an acid delivers protons. And then we get CH3NH3 plus aqueous plus H2O. What is the state of H2O? Okay, it will always be liquid. Okay, H2O is liquid. Okay, what's the conjugate acid and conjugate base here? Partners. What's the partnership here? Okay, this is a base. Amines are going to be a base. What is its conjugate acid? Okay, CH3NH3 plus. This is called methyl ammonium, but you do not have to know that. Okay, if this is the base, what will this be? Okay, obviously H3O plus is an acid. Okay, and what is its conjugate base? This one. Okay, so conjugate acid, conjugate base pairs. All right, let's figure out the concentrations after mixing here. So let's go over here. Okay, let's first do the H3O plus or H plus. Okay, we have 25 mLs of 0.2 molar HCl. And what's our total volume here? Okay, 75 mLs. Okay, 50 mLs in here, plus the 25 from our equivalence point volume. So what's 25 times 0.2? Is that 5? 25 times 0.2. Is that 5? Yes, I was right. Huh. 5 divided by 75, that's too much math. 0.0667 big M. Okay. What do you think the concentration of the CHNH3 is? It's the equivalence point, so what is its concentration? The same, 0.0667. All right, so here, CH3NH2. Sorry about that. Our concentration of CH3NH2 is 0.0667 molar. The concentration of H3O plus is 0.0667 molar. Okay, we don't care about water. This is 0. So how much of the strong acid would eat up this weak base? How much would it do? Will it eat up? Okay, it will eat up all of it. How much is all of it? 0.0667. Okay, we have plus 0.0667 here. Okay, so we have a problem. Okay, we have 0 and 0. How are we going to get the pH? Okay, what reaction? Okay, we'll use the reverse reaction this way. Okay, so we'll use the reverse reaction. All right, so the reverse reaction is going to be CH3NH3 plus H2O liquid. Okay, so this is going to donate the proton, giving us H3O plus CH3NH2 aqueous. Okay. So does anybody know what type of reaction this is? What type of reaction is this? What type of K is this? K what? KC, KEQ, KW, KC, KB, not KB. What would it be? KA. Okay, so this is KA. Okay. This is the reaction that represents the Ka. Okay, here you have the base reacting with water, giving you the conjugate acid and conjugate base. So this is the Ka. So the Ka for CH3NH3 plus is, I have it here. I'll give you this on the exam, so do not memorize it. found 4.4 times 10 to the minus 4. Okay, so I'll give you this on the exam. Okay, so this will be given. Ka or Kb will be given. So this will be given to you. Alright, so this CH3NH3 plus is 0.0667. Okay, we don't care about water. This is 0, this is 0. Bless you. Minus x plus x plus x. So 0.0667 minus x plus x and then plus x. Okay, so we're using the reverse reaction and then doing this type of ice table. Okay, we'll plug that into our Ka. Let's see here. So Ka is equal to H plus, which is the same as H3O plus, times CH3NH2 divided by CH3NH3 plus. Okay, so let's use the next sheet of paper here. Ka, which I'll give you guys, is 4.4 times 10 to the minus 4. H plus is x, CH3NH2 is x, x times x is x squared, divided by 0.0667 minus x. And then here we'll use our low ionization assumption and assume x is small. Alright, so 4.4 times 10 to the minus 4 times 0.0667. Okay, we'll square root that. And what is this on our calculator? Square root. I'm getting 0.00542, something like that. Okay, 0.00542 molar. Don't forget the molar. Okay, that's x, but what does this x really mean? Okay, this x is actually this x, which is the concentration of H3O plus. Okay, so we can calculate the pH now, because we know pH is equal to minus the log of H plus concentration. So minus the log of 0.00542. Okay, what do you guys get on your calculator when you do that? Minus the log of this number, 2.27. 2.27 is what I'm getting. Okay, as long as there's no objections, we'll go with 2.27. Alright, so this is at the equivalence point. You guys need to remember to use the back reaction. Okay, and you're either going to use Ka or Kb. Okay, in this particular problem we used Ka.
So we use Ka because that CH3NH3 is like acid.
Yes, it's a weak acid reacting with water to give you H3O plus. Anything that gives you H3O plus from water is a Ka equation. Okay, so why is this a Ka? Which I'll give you all the Kas, okay? I'll give you the Kas. Why is this reaction that's, the form of Ka? Because you have the water and then you have the H3O plus. Okay, and then this weak acid gives rise to its conjugate. So that is the Ka. Okay, what would it be if it were Kb? It would be the water, and what would you get? Not H3O plus, but if it was a Kb. OH minus. OH minus, that's correct. Yeah. All right, so titration problems. I think next week you guys won't have a lab. You won't have a wet lab, but you have a long set of practice problems, so you can work together, work with your group, teach it to one another, and you can turn those in. It's a lot of problems. I should also tell you this, that we can skip KF. Okay, complex ion formation I will not cover, but you can skip those type of problems. This is for next week. Okay, so work on those problems with your group. You do not have to update your lab notebook. You just turn in a hard copy to me or whatever. You turn in a hard copy, and then I'll give you the 100 points. Okay, you and your group. Okay. If you're going to do this together, make sure you know how to do the problems. Like, if you're going to split them up, make sure you know how you do your problems, and then the other sets of problems. Basically, know how to do these problems. That's all. Okay? If you split it up. All right. So that's next week. So next week we do not have to meet up here. Okay. So that may be good news for some of you, or it may be bad news because you don't want to do all these math problems. So, yes. You can come to a lecture, but don't have to come to lab. Yeah. Or you don't have to come to lab, because I figure you can do this at home, or you can get together and do this. All right, so the final part here of this chapter, chapter 16, like I said, we're going to skip complex ion formation, so we're really going to go up to page 13. No, maybe 15. No, 16. We'll go up to page 16 here. We'll go up to page 16. All right, solubility equilibria. Okay, this means KSP. This is a new type of K that I'd like to teach you guys. And KSP stands for the solubility product constant. So how do you know whether it's Ka, Kw, Ka, Kw, Kb, okay, or KSP? So if you're looking for KSP, what will be in the reactant side? Solid. So it's a solid that's in an equilibrium with its reactants. A solid that's in an equilibrium with its ions. Okay, we call this, Alex, since you call it solids, we call these sparingly soluble solids, okay, because they are in equilibrium with the ions. Okay. Sparingly soluble solids. So if you see the solids here, and what else makes you sure that this is an equilibrium and not a one-way reaction? Okay, the back and forth arrows. So the solid that's in an equilibrium with its ions. Okay, these are KSP. So look at some of these KSP values. Okay, they're very, very small, 10 to the minus 10, 10 to the minus 8 for lead, fluoride. Calcium phosphate is 10 to the minus 26. So these are very, very exceedingly small numbers. So that implies most of the equilibrium favors the left. Okay, it favors the left. But some of it does go this way. Some of it does go this way to give you the ions back in solution dissolved in water, and the ions back in solution dissolved in water. Okay, so that's what we're interested in. This is called the KSP. We call it for sparingly soluble solids. Let's go to page 10 here. All right, so question is, will it precipitate or not? Will it be a solid or will it stay in solution? Okay, for that we can use what's called the Gator rule. Okay, do you remember the Gator rule? Okay, so we will use reaction quotient Q and compare it to KSP. In the Gator rule, we're going to have to put, as a caveat, put Q first, then compare it to KSP. Otherwise, what I'm telling you is not right. But if you put Q first, then compare it to KSP, and then we can determine whether it will precipitate or not. Okay, whether it will be a precipitate or not a precipitate. Okay, so how does this work? Okay, for a KSP problem, okay, there's three scenarios that could emerge. Okay, one is this Q can be greater than KSP, the Q can equal KSP, and then Q can be less than KSP. Okay. All right, so let's look at this equation here. Okay, here we have silver chloride in an equilibrium with Ag plus and Cl minus. Okay. Right, so what happens if you calculate Q and it's greater than KSP? Okay, where are the alligator jaws pointing? To the left. Okay, so will you get a solid formation? Will you get a precipitate? Yes or no? Yes. Okay, so put Q first, you will get a precipitate. Okay, I'm going to call precipitate PPT. Okay, if Q is less than KSP, okay, where do the alligator jaws point to? The left or the right? The alligator jaws point to the product side. Will we get a precipitate or will we not get a precipitate? Not. Oh, so a precipitate will not form. Okay?
And we'll get the ions.
You'll get the ions. Okay? Okay, you'll get ions in solution. Okay, so basically water, no reaction.
And you said on the last page, because the KSP is small, that usually it favors the reactants?
Yes. Yep. That's why they're sometimes called sparingly soluble solids. They sparingly are soluble. Okay, very sparingly. Mostly there will be a precipitate, yeah, because these numbers for the KSP equilibrium constant are so small. If they were large, it would favor the, forward direction, but they're small. That doesn't mean we ignore the problem. It just means that some of it will go here, but not a lot. Some of it will go at the back, or this way. Okay. Right, what happens if Q is equal to KSP? Neither happens. We call this a saturated solution. So 1 drop of Ag or 1 drop of Cl minus would cause the precipitate to happen. So this is called a saturated solution. Okay. So those are the three scenarios that could emerge. Okay, Q, if you remember, is called a reaction quotient. Okay, we use Q to compare to KSP to determine whether the reaction will form precipitate and form the solid, or whether it will not form the solid. Okay, that's all it does. All right, so we can do, let me see our next page here. Okay, let's do this problem here, and then we'll see how far we can get. All right, so let's look at this one here. All right, so the KSP you can look up is 1.6 times 10 to the minus 10. Okay, that's what KSP is, 1.6 times 10 to the minus 10. Okay, this is something that I'll give you. You look it up in the book, okay? In the back of the book or something. It's a constant, the solubility product constant for silver chloride. All right, so now we'll do the KSP expression. Okay, products over reactants. Okay, why did we skip AgCl? Okay, because it's a solid, okay? So this is going to be, some of it will go this way. We don't care about the solid, but some of it will go this way, so we call it plus S and then plus S. Just one S because it's 1 Ag plus. One S here because it's 1 Ag plus. So we're going to plug in S here and S here. So it's S times S is going to equal to the constant for AgCl, which is 1.6 times 10 to the minus 10. Okay, S squared is equal to 1.6 times 10 to the minus 10. So the solubility of both Ag plus and Cl minus is going to be the square root of 1.6 times 10 to the minus 10. And what is that on our calculator? .3 or something, 1.26 times 10 to the minus 5. Okay, so this is how you do these KSP problems. Okay, and molar. Okay, molar. So this is how much moles per liter of Ag plus goes back in here. If you have 1 liter of this solution, most of it will be Ag solid, AgCl solid. And if you have 1 liter of this solution, most of it will be Ag plus, AgCl solid, but 1.26 times 10 to the minus 5 molar Cl minus will be dissolved in water. So this is how we do these types of KSP problems. So we'll have some more practice with this a little bit later on. Let's see if we can do the last 5 minutes of this problem. Page 11 here. All right. All right, so the solution is here, but we'll do it together. All right. All right, if 2 mils of 0.2 molar NaOH are added to 1 liter of 0.1 molar calcium chloride, will you generate a precipitate? Okay, will you get a precipitate that forms? If 2 mils of 0.2 molar NaOH are added to 1 liter of 0.10 molar calcium chloride, will a precipitate occur? Okay, what will be that precipitate? Okay, so NaOH is Na plus and OH minus, and then calcium chloride is calcium plus 2Cl minus. All right, so the precipitate is actually, when these two react and mix together, the precipitate is going to be calcium hydroxide, which has a KSP of 8 times 10 to the minus 6. Right, so let's write the equation here for the KSP, calcium hydroxide solid, okay, is in an equilibrium with calcium ion, which is +2, plus OH minus ion. Okay, this is aqueous, this is aqueous. We have to balance this, so it'll have 2. Okay, 2. Let me write it again here. Okay, this is the one that has the KSP of 8 times 10 to the minus 6. All right. So let's do a concentration after mixing. Okay, we'll first do OH minus. We have 2 mils. 2 mils. I'm going to convert that to liters. So divided by 1,000, 0.002 liters times 0.2 molar. And what's our total volume? 1 liter plus 0.002 liters is 1.002 liters. Okay, everyone see that? Okay, 0.002 liters plus 1 liter is 1.002 liters. Okay, total volume after mixing, the liters canceled. So what is this on our calculator? Okay, I'm getting about 0.000399 molar. That's the concentration after we mix this. The concentration of the calcium ion coming from calcium chloride. Okay, we have 1 liter times 0.1000 molar. Okay, our total volume is 1.002 liter. So 1 times 0.1 divided by 1.002. .0998 molar of calcium ion. Okay, so this is what we want to plug in to see if it's enough to make it precipitate. Okay, so we'll plug it in here. KSP is equal to calcium ion plus OH minus squared. Don't forget to square it. And I think we have to go here. All right, so this is going to be plus S, and how much will this be? Plus 2S. Okay, so KSP is going to equal to S times 2S squared. And then here we have KSP is S for the calcium ion, which is 0.0998. And 2 times S. 2 times S. 2 times S for the hydroxide ion, and we have to square it. Okay, square it. Okay. We will ask ourselves the question, if this equals KSP, which is 8 times 10 to the minus 6, we have a saturated solution. But if it doesn't, if it does not equal, if these concentrations does not equal KSP, which way will the reaction shift? Okay, will it shift to the left side to give us solid calcium hydroxide, or will it shift to the right side to give us no calcium hydroxide solid? Okay. So we calculate this, we compare it to QSP. We put Q first if you want to use the Gator rule, but I'm past the time now. It's about 1:51, so we'll finish this problem on Friday, and then I'll see you at lab at around 2 o'clock.